All right. So the function was. Screw 2x. Yeah. So fx was 2x minus 2xy. So fxx is what? Fy was 4y minus x squared. So fyy 4. Cool. So concavity in the purely y direction seems to always be positive. Okay? But it's concave up somehow always in the purely y direction. And then what's fxy? How do I calculate fxy? I look at this as, so anytime you take a derivative, you've made its own new function. So this just says do the partial of y with respect to, do the partial of y of this function. And of course it's just going to come out to be negative 2x. I like it. For most functions, it doesn't matter what order this is done in. But just be careful and just do it in that order just in case you get a funky ass function. Negative 2x. So now I can evaluate all of these at the points, at each of the points. Right? So at 0, 0, what'd you get for fx at 0, 0? I'm sorry, fxx? 2. Alright. And fyy? 4 is always 4. And then fxy? Yeah, fxy there would be 0. I like it. So then d would be 8. Oh, my d's gone. Too bad. D is going to be 2 times 4 minus 0 squared, so 8. Greater than 0. And fxx was greater than 0. Therefore, what's true at that point? Minimum. Minimum at 0, 0. What is the value? What is that minimum value?
0.
0. Yeah. If your inputs are 0, 0, the output is a minimum. Well, if your inputs are 0, 0, the output is 0. Okay, lock it. Now be careful. Does that mean that's the lowest that this function gets? That's not an absolute minimum. There are absolute maxes and mins, and I don't know if you remember from calculus, but that was the nice one, because you just did the function values and see who wins. It's going to be a little bit more difficult for us now because our inputs live in a plane. Oh shit. So we're going to get to that in a bit. What about this guy? fxx?
0.
0. fyy? 4 everywhere. Yeah, and fxy?
Negative 4.
Yeah, negative 4. Let's see. Yeah, okay. So then when you do this, what's d come out to be? 0 minus 16. So negative 16 is less than 0, so it doesn't matter that that was 0. Saddle point. And you get the same kind of thing for the other one. Is that cool? So somehow, I like the question, because it's easy to see that one saddle, but now somehow I got a 2-seater, right? There's 2 places to put your butt. So here, let me see if you guys can see what I've done here. I've got it to the point where I've zoomed in enough, so I'm looking at the point, which point was I looking at here? Negative 2, oops, got it. Negative 2, 1. So here's the x-axis, negative 2, and the y-axis, so 1 would be right here. So it's that middle point there. And do you see how, if I look at it this way, it looks like it's a min? It's not as clearly defined. For the saddle point one I gave you earlier, they were following the x and y axes. It was kind of easy to give them. Now this is kind of diagonal to those. This is the cutting down the middle, but it's still the same idea. I've got an up parabola there if I look at it dead on from this direction. If I look at it dead on from the other direction, let's see if I can look at it dead on. Where else? I've got a down parabola here and an up parabola there. You guys see the ends? Looks like a manta ray. Dipping down right there, and you can see it there a little bit. Dipping down, and if I look at it the other way, Just open up. So it's still the same idea. At negative 2, 1 and 2, 1, if I zoomed in, it would still do that same kind of weird thing where it looks like this way in one direction and this way in the other direction. So these two things are going on at the same time. That's not easy to do. Yes or no? Yes, no? I mean, with one saddle point, it's easy to see, but I can have multiple places where it has this shape here and this shape this way. That can certainly happen multiple times. It can happen an infinite number of times, to be honest, depending on how funky my function gets. All right, so you got infinite. If you had infinite horses, you're gonna big old group with one giant saddle, and I don't know. It's a very strange scene. Let me zoom back out so you see what this looks like, kind of total. Am I zooming out or in, Josh? There you go. Maybe just make these big. Woohoo! Where am I going? Oh, this is worse. There we go. So that's sort of like what the function looks like total. But then you kind of lose. It's because really close to those points, it's not changing very much. So it's a very subtle saddle point, very subtly going up this way and going down this way. But it's completely possible to have multiple saddle points on one surface. You don't like that at all, do you? Why not? What's wrong?
It just doesn't. I don't know. Like it doesn't make sense.
So again, if I zoom in, if I zoom in on the other one, what was the other one? 2. The other one's 2, 1, right? 2. Make my y. So what I'm trying to do is I'm trying to change the y so that it's more centered around 1.
That much different.
There. So again, here's the point 2, 1, and it's analogous to the other point we looked at. This way it's sloping, it's got a concave down, and this way it's got concave up.
Wouldn't it just that be at 1 point?
No, the other one I had earlier was at negative 2, 1 on the same surface. So it's not the. I wish there was a single zoom out button, but I have to zoom out by doing each one of these individually. It really, really sort of sucks. Let's see if I can do this.
Okay, well then seeing it that way.
So it's just a mirror image almost. So of course anything that happens over here is going to happen over there the same way. So you can imagine with trig functions existing, I could set something up possibly using trig where it's periodic, and I can have an infinite number of saddle points because it's going to repeat whatever happens here is going to repeat it infinite number of times. Yeah, okay, I like it. So it's easy to imagine one saddle. You've never seen like 2 saddles connected because the horses would be like, what the hell's going on with this shit? But again, it's just because it's symmetric. So if there's a saddle point there, it's got to be a saddle point there. I like it. And this is why Wolfram Alpha, or something else, I think somebody else sent me a link to an online 3D plotter. You need to find an online 3D plotter or some way to plot 3-dimensional figures and turn them to be able to really make sense of a lot of things in this class. I mean, that's just the way it is. I don't know how I passed this class way back before we had any of this shit. I mean, the internet was just being invented by Al Gore somewhere. Sorry. And so we didn't really even have, thank God, we didn't have social media. How did we survive? Facebook was years away. Right? We actually talked to each other directly. It's crazy. I liked your shirt. We didn't have to push a button. It was crazy. All right, Jeff, stop. All right. So what about the second problem? Have you guys started that one? Do that problem. Do it. And just to remind you guys, what is the distance formula? In 3 dimensions, it's the same as 2, just with one extra dimension thrown there, right? And just to remind you guys, the beautiful thing, if I were you, I would be very concerned about, you got y's and you got z's, right? The square root makes the derivatives you have to do disgusting. Let you start. Now, if I can minimize the inside, that will minimize the square root of the inside, won't it? So I minimize d squared. So here's my little niceness for you. I'll tell you that. Dear God, the derivatives would be horrendous otherwise. But if I make d squared smallest it could be, then obviously I've made the distance the smallest it can be. Hopefully obvious. I mean, this is the same thing you did back in Math 180. It's exactly the same thing you did back then. You know, like that was about 7 years ago, man.